Multiple regression, in many ways, is the cornerstone of business analytics because it allows us to perform a much more in depth analysis when examining the relationship between y and x in order to account for lurking variables. And then also, it gives us the ability to make the predictions for y by synthesizing many sources of information simultaneously. And that's typically what we need to do. If we really want to hone in on the relationship between y and a particular predictor, x here, then we have our work cut out for us because we know that in general there are many predictor variables that are responsible for variation in y values among individuals. And if we just focus in, say, on a simple linear regression or a simple analysis of an association between y and x, that leaves us open to having a biased picture. And that's because any other source of variation that we haven't included into our model is a lurking variable and can otherwise provide an alternative explanation for the relationship that we see between y and a particular variable of interest. So if I really want to study the relationship between salary and experience, then I need to account for other sources of variation in salary. Variations in individuals' educational values, variation in how long the person's been working at the company, etc. So to get the best view of the relationship, we need to account for these other lurking variables here, these other factors, before doing that. Likewise, if I wanted to study the association between college GPA and race, I need to take into account lurking variables, other sources of variation for GPA among individuals, such as socioeconomic conditions, how many hours people are working, quality of high schools, etc., all other factors that influence GPA. And likewise, if I'm in the health sciences and I really want to study the link between obesity and heart disease, well, what I need to make sure is I account for other lurking variables. I need to account for other reasons people might have heart disease, differences in diet, exercise routine, maybe even geographic location, etc. And with predictive modeling, I have many sources of information available to me to help make my predictions. Why don't we use all of that at the same time? So to predict salary, we could use information about education experience, months at the company, also location of the job title, etc. Let's use all that information to make the best prediction possible. To predict how much someone's donating, let's not just use information about, say, past donation amounts, but also their income, home value, gender, graduation year, etc. simultaneously. So we very often have many different predictors of our y variable, and multiple regression allows us to use them all. So our multiple regression model says that an individual's value of y is more or less a weighted sum of its predictor variables with weights equal to the coefficients, and individuals differ from what the regression would predict, just plugging in the x values into that equation, by a random amount, epsilon. The disturbance, and this represents just the random deviation of an individual from the overall average value of y at that combination of x's. So the assumptions behind this multiple regression model, when we know we can use it, is when the average value of y has a linear relationship with each predictor variable, and we see that the typical difference between an individual's y value in reality and the value predicted from the regression, just by plugging in its x values in there, that typical difference, the typical size of the residual, should be the same regardless of that individual's characteristics. In other words, the typical size that the error that the model is making is the same for all individuals, regardless of their x values. And then finally, when I do look to see how far individuals deviate from where the regression predicts, the overall distribution of those residuals is well described by a normal distribution. So checking the assumptions is even more important for multiple regression because there are even more things to check. And so oftentimes the first stop is looking at the scatterplot matrix. Here we're trying to predict the closing price of Alcoa stock based on the closing prices of 3 other stocks 2 days beforehand. And the top row gives the relationship between y, Alcoa, and each of the 3 predictors. And it's nice when we see nice linear relationships here between y and the predictors, but with multiple regression it's not a requirement, because it could be the case that the reason we see kind of weirdnesses going on in the relationships is that there are interactions going on between the variables. But this gives us an idea for, just by itself, how is Alcoa related to the closing price of Apple stock 2 days beforehand. And then it also gives us an idea for how the predictor variables are related to one another as well. Because it turns out the degree to which the predictors are related affect how confident we are in our estimated coefficients. All right, so we can get the regression model fitted. We can come up with the best estimates of those coefficients using least squares criterion, and we need to make sure that the model seems to be an accurate reflection of reality to actually use. So we need to look at the residuals plots like we did with simple linear regression, as well as the histogram and more specifically QQ plot of the residuals. And we also have an additional set of plots to check, the residual versus predictor plots. We need to make sure that the errors the regression is making, kind of what's left over after we fit the model, doesn't have any leftover pattern with each of the predictor variables as well. If there are patterns, then the relationship between y and that particular predictor isn't completely described by the model, and it needs to be adjusted. So with the salary model, here's the residuals plot, the residual versus the predicted value, and we don't see any sort of leftover pattern. Our model seems to be explaining the relationship adequately. No curvature, no unequal vertical spread here. And the residual versus predictor plots, residual versus education, residual versus experience, look fine as well. No overall curvature, indicating that I've more or less captured what there is to know about the relationship between salary, education, and experience. All right, so what specifically do we look for? How do we know when the model is a reasonable reflection of reality? Well, the first thing we check for is the linearity assumption. So we look at the residuals plot, the residual versus predicted values, and we're checking to see if there's any leftover curvature. If there is, there's some systematic component in the relationship that isn't captured by the model, and it needs to be adjusted. We also check to see if there's any curvature in the residual versus predictor plots. If so, there's something left over about the relationship between y and that particular predictor that isn't captured by the model, and it needs to be adjusted. The next thing we check is the equal vertical spread assumption. We need to make sure the regression model is making about the same typical size of the error, regardless of the characteristics of the individuals. And so when we look at that residuals plot, residual versus predicted values, it should have roughly the same up and down deviations everywhere, indicating that the typical prediction error is the same regardless of the y value we're trying to predict. It's not the points aren't clustered closer to the regression in some locations than others. And then finally, we look at the QQ plot to see whether or not the distribution of the residuals is matching up well enough to a normal distribution, just like what we did for simple linear regression, and we have to make sure that's the case. So, like with simple linear regression, there are statistical tests to check these assumptions, but the failure of them doesn't tell us anything interesting. We already know our model is an oversimplification of reality. It just can't be too wrong to use. So the guideline is if there are very few data points, less than about 24, we need to abandon the model if the tests are failed. The p-values are less than 5%. And if the tests are failed, but we have a lot of data, p-value is less than 5% here, we go and check to see if there's any obvious painful violations in the plots, because small violations are okay and aren't going to affect our estimates too much. One additional complication in multiple regression is our outliers. So we've seen that particular points can actually have a lot of influence over what the coefficients in the regression model are. And detecting outliers in multiple regression can be difficult because they can have fairly ordinary values for each one of the predictor variables, and they might even have ordinary pairings, but they might be unusual in some combinations of 2, 3, or even more predictors. So outliers can be hidden in box plots for individual predictors, or even scatter plots looking at relationships between predictors, and so we have to have another method for detecting these potentially influential individuals. So we look at two things. We look at the point's leverage, basically how far away is that point from the center of the predictor data cloud, the kind of the data cloud describing how all the x variables are related, and that distance is measured with respect to the shape of that data cloud. So these 2 points are the same ruler distance away from the center, but this one has a higher leverage because given its shape, this elliptical shape, it's farther away from the center. So what we find is that only points with a large leverage have the potential to be influential. And the second part of the equation is how far away is that point from where the regression was going anyway. We need to look at that point's deleted studentized residual. Basically, how far away is that point made or from the regression made on the data points without it. So in our outlier demo here, we saw that the black line corresponded to the regression model built without the red point. So here's the line without that red point. And then with that red point, we see the lines changed quite a bit. The deleted studentized residual is the distance between the red point and the black line here. Basically, the residual with respect to the model built on every data point except for that red data point here. So when we have a large deleted studentized residual, when it's far away from where the regression was already going, and the point had a large leverage, a very unusual combination of x, then the point is influential, and we have to worry about the amount it to influence the coefficients. So it has to have both a large leverage and a large deleted studentized residual to be influential, and we can detect them with an influence plot, basically a plot of the leverage going left to right versus deleted studentized residual going up and down. And so influential points live in the bottom right-hand rectangle and the upper right-hand rectangle to the right of this vertical line indicating high leverage, and above or below these horizontal lines indicating large positive or large negative deleted studentized residuals. So we see that actually in this data set there's quite a few influential rows, and we should go back to check to see, are there typos anywhere? If so, we should delete them. All right, so once we fit the model and we've confirmed that it's a reasonable reflection of reality, we need to talk about it. What do the numbers mean in the regression model? What do those coefficients mean? So this is one of the more tricky parts, and this is one of the key things I want you to be taking away from the class, because it's often done incorrectly, even by professionals that work in the field. So the intercept term doesn't really tell us anything interesting. That's just the average value of y in the population among all individuals who happen to have each predictor variable equal to 0. Who cares? It doesn't really matter. It's the coefficient of the predictor variable that encodes all the interesting tidbits of information. So how do we interpret a coefficient? Well, what we say is that two otherwise identical individuals who happen to differ in xi by 1 unit are expected to differ in y by bi units. If that number is positive, the individual with the larger value of xi is expected to have the larger value of y, etc. Now, a key part of this interpretation is this otherwise identical clause. And what that means is that those two individuals that we're comparing that happen to differ in xi by 1 unit had the exact same values for all of the other predictors. It doesn't matter what those actual values are, they just have the same. So for instance, if I try to predict salary from education experience in months, here would be my regression equation. I can recover that just by writing out y equals and then reading out these numbers. The intercept is 2864 or 2865 plus 93 times education plus 11 times experience plus 13 times months. So what does this number mean in front of education? Well, what that tells me is that if I were to compare two individuals that happen to differ in education by 1 year, but who happen to have the same values for experience and same value for months, I would expect those two individuals to differ in their salary by $93. Since it's positive, the more educated person is expected to have a higher salary. So we need to be very cautious about how we interpret the coefficients of a model. The coefficient is very precisely interpreted. It means something very specific. It's the expected difference in y when two individuals differ in xi by 1 unit, but who are otherwise the same with regard to all the other predictors in the model. And just like with simple linear regression, the coefficient is not a comment about what happens to an individual's value of y if their x changes up or down, because regression is not a physical law here. Regression does not describe what happens. So one quirk about multiple regression is that coefficients are model dependent, and this can be very confusing when you're first learning multiple regression because you'll get different values for the coefficients of a particular predictor variable based on what other predictors are in the model. So what's the correct value for the coefficient? And the answer is that they all are correct, because when we interpret that coefficient, we're saying two individuals that differ in xi by 1 unit but whose other values of x are otherwise identical, well, those two individuals are expected to differ in y by bi units. So when we change what x's are in the model, when we change models, then essentially those two individuals that we're comparing that happen to differ in xi by 1 unit are going to differ in other quantities. So those two individuals that you're comparing change between models, and so not too surprisingly, the expected difference in y between those two individuals are going to change as well, because fundamentally those two individuals we're comparing have different characteristics from model to model. It turns out the amount of this change from model to model depends on how correlated the predictors are, in fact. So why might this be the case? Well, imagine trying to predict body fat percentage based on someone's abdomen size. So if we just fit a simple linear regression and look at the coefficient of abdomen, it's basically saying that's the expected difference in body fat percentages among two individuals who happen to differ in abdomen by 1 unit. Well, one thing I know is that body measurements are correlated with one another. In fact, abdomen circumference is correlated with neck circumference. So what that means is that, all right, if I find two individuals that differ in abdomen by 1 unit, well, because that's correlated with neck circumference, those individuals are also going to be different in neck circumference. So if we fit a multiple regression model, or sorry, when we look at that simple linear regression model, and we're just comparing two individuals that differ in abdomen by 1 unit, that coefficient tells us the expected difference in body fat percentages. But some of that coefficient of abdomen is kind of due to the fact that those two individuals are also different in neck. So some of that coefficient in abdomen, when those two individuals differ in abdomen by 1 unit, they're also simultaneously being different in neck. So some of that coefficient's kind of due to neck circumference as well. So when we fit the multiple regression model, when we actually add neck into the model, then we get a much clearer view over how the body fat percentage is expected to differ between two individuals who just differ in abdomen. So by throwing neck into the model, we're able to account for this lurking variable, another reason that body fat percentages vary besides just abdomen, because the coefficient of abdomen is now comparing two individuals that differ only in abdomen circumference by 1 centimeter, but who have identical values of neck. So the part of the variation in body fat percentage that's attributable to neck differences when they differ in abdomen is taken away, and I get a peer review of the relationship between abdomen and body fat percentage. So one of the key insights is that when you do have very highly correlated predictors, and this happens a lot, the values of the coefficients can change drastically, sometimes counterintuitively between models. Doesn't mean it's wrong, it's just illustrating something actually pretty insightful that you might not have been able to realize otherwise. So here's an example of that. If I fit a simple linear regression predicting body fat from neck circumference, I find the coefficient is positive. Two individuals that differ in neck circumference by 1 centimeter are expected to differ in body fat percentages by about 1.6%. All right, well, if I throw in abdomen into that model as well, and now predict body fat from both those predictors, I find the coefficient is negative. So two individuals that differ in neck circumference by 1 centimeter, but who happen to have the same abdomen circumference, well, they're expected to differ in body fat percentages by 0.9 percentage points, with actually the person with the thicker neck having the lower body fat percentage. And that feels weird because we know that people with progressively thicker necks tend to be heavier, have more body fat. So this seems to fly in the face of intuition, but it really doesn't because of the specific interpretation of the coefficient. We're comparing two people with identical abdomen sizes. So in some way, it's kind of weird to have two people that differ in just neck but have the same abdomen. It's probably the case that these two people are differing in muscle masses. Maybe one of them is a bodybuilder, their neck is really thick because they've worked out a bunch and so they just have a really thick neck. And muscle weighs less than body fat, so it actually would make a little bit of sense that the person with the thicker neck might actually have the smaller body fat percentage because they just have more muscle. So there can be surprising bits of insight yielded from your data when you start looking at the coefficients in a multiple regression model. All right, so how do we know when a multiple regression model is fitting the data well? Well, we don't look at R squared. The reason why is that R squared always gets larger when we put an additional predictor into the model, even when that predictor has nothing to do with Y whatsoever. So what we do instead is look at a value called R squared adjusted, which starts out with the value of R squared and then applies a penalty term based on the number of predictors in the model. So in order for the value of R squared adjusted to increase when a new predictor is added, basically that predictor needs to be worthwhile. It really needs to contribute additional information about Y. It needs to increase R squared large enough to offset the penalty due to the added complexity. So if we're going to compare different models, different multiple regression models, and see which one is better, R squared adjusted is the thing we want to compare. We can also compare the root mean squared errors of the models because that actually also takes into account the complexity of the model, the number of predictors as well. The root mean squared error is only going to improve if the added predictor actually really contributes some pretty important information about a Y. The root mean squared error will actually get larger if you add in a junk predictor. All right, another key thing is talking about the significance of a multiple regression model. And we talk about two things, the significance of the model itself and significance of the individual predictors. And so we're going to talk about significance in terms of the sum of squared errors that the regression makes. All right, so if we talk about whether or not the regression model itself is statistically significant, what we do is we look to see what the reduction in the sum of squared errors is when we go from the naive model to predicting Y to the regression model predicting Y. the regression model has more freedom to fit the data, so there's always going to be a reduction. And the question becomes, is the reduction in the error large enough for me to be convinced that there's some useful information in the model? So basically, I need to figure out what reductions in sum of squared errors could happen by chance, basically with a model full of predictors unrelated to y. And that's what the p-value of the significance test is actually looking at. It's evaluating the probability that you would get a reduction in the sum of squared errors at least as big as the one that your model got just by random chance. So if the p-value of the regression model is less than 5%, we say it's statistically significant. And what that means is that it's predicting y better than the naive model, basically using no information about x alone, or it's also better than a model full of predictors unrelated to y. And once again, it's not a physical law. It doesn't prove a causal link between y and any of the predictors in it. It's describing the difference in the average value of y between different individuals. So where do we find this information about the significance of the model? Same place we did with simple linear regression, the bottom right-hand number here. In this case, the p-value is less than 5% for this regression model. So there's something in the model that's yielding some pretty significant information about predicting y. All right, significance of predictors is one of the other key things I want you to be taking from this course. And if the model is significant, there's something in it that helps to predict y, and we might be able to answer a little bit about what predictor helps. So when we look at the p-value of an individual predictor in the model, and these are the numbers on the far right in the row labeled after the name of the predictor, these are telling us something very precise and important. Basically, if we look at the p-value of that predictor and it's less than 5%, we say that that predictor is statistically significant. What that means is that when we add that predictor into the model with all the other predictors in it, we get a significant reduction in the sum of squared errors, larger than what we would have gotten by adding in a predictor unrelated to y. So the statistical significance of a predictor in a multiple regression model is not a comment about whether or not y and that x have any sort of relationship. It's only a comment on whether adding that predictor into a model that already contains the other predictors significantly helps to improve the prediction accuracy, reduce the sum of squared errors. So in other words, does adding x into that model yield significant additional information above and beyond what the other predictors already offer? So you can run into some kind of weird situations where in a simple linear regression, a predictor might be significant, but in a multiple regression, it's not. How do we resolve this paradox? Well, if we predict the number of wins of an NFL team by the number of offensive total plays it makes, we see that the regression is highly statistically significant. We do much better predicting wins from this variable than some variable unrelated to the number of wins. But if we try to predict the number of wins from also the offensive total yards of that team, what we find is that the predictor, offensive total plays, is no longer statistically significant. It's now 0.17 and not significant. So what's the deal? Does this variable have information about wins or does it not? And the answer is, yeah, it does, because we saw in the simple linear regression it was statistically significant. It adds significant information about the wins of a team. The fact that it's not significant in the multiple regression model just says it doesn't add any additional information about the team's wins above and beyond the information provided by the offensive total plays. In other words, what it's saying is that the information contained in offensive total plays is redundant with the information that offensive total yards has. Once I know offensive total yards, I don't also need to know offensive total plays. That doesn't add any additional information about the number of wins. All right, so one thing that we see is that the significance of predictors are model dependent. Might seem a little confusing at first, but it's exactly what we'd anticipate when we really hone in on what the interpretation of significance means. So we might find that x is significant in one model, but not in another. And all that means is that adding x into the model for which it was significant adds some significant additional information about y above and beyond what the other predictors are offering. If we add in x, or if we find x is not statistically significant in a model, that just means adding it to that model didn't increase the amount of information about y above and beyond the information we already had. That information in x is redundant with the information provided by the other predictors. All right, we can also see the case where maybe x is not significant in a simple linear regression, but it is in a multiple regression model. That's kind of weird. And once again, that does indicate that x does contain some useful information about y, because it is significant in one of these models. In this case, it just means that the variation in y attributable to x is probably relatively small compared to other sources of variation. So, in other words, in that simple linear regression, the association between x and y is being washed out by stronger associations, some lurking variables. And it's only after accounting for those lurking variables, those other sources of variation, by putting them into the regression model, does that association stand out. And in fact, that's what happens with the salary data. If we just predict salary from experience, we don't find a statistically significant relationship. So experience isn't predicting salary by itself any better than the naive model. But it is statistically significant in a model that also has education in it, implying that once we've accounted for the variation in salary that can be attributed to differences in employees' educational levels, then the information provided about experience is significant. It helps us to predict salary better than just some unrelated random predictor. All right, so be very careful about the interpretation of coefficients and significance in a multiple regression model. We know that if a single predictor is non-significant, we can drop it from a model because it doesn't add anything to it when we add it to a model with all the other predictors in it. Can we just drop all the non-significant predictors in a model? Well, the answer is no, because we know that p-values are model dependent. If we drop one predictor, the rest of the p-values are going to change, and it might be the set of non-significant predictors changes when we drop a single one. So if we want to know whether a set of predictors are statistically significant, if we can drop them all from the model, we perform the partial f-test. So just know we fit the model with all those predictors and then without those predictors, and we see if the decrease in the sum of squared errors when we go from that simpler model to the model with all the predictors, we look to make sure that that decrease in sum of squared errors is statistically significant. All right, one of the last things, how accurately are we estimating the coefficients of the regression model? Well, it turns out that that answer depends on how much correlation we have in the predictors. In the formula for the standard error of an estimated coefficient, we have this chunk 1 minus ri squared. So the standard error of the coefficient bi depends on this value ri squared. What this value ri squared is the value of r squared for a multiple regression trying to predict xi from the other predictors. So if ri squared is large, that means that you can predict xi pretty well from the rest of the predictors. What that means is that the resulting standard error, the precision that you get with the corresponding coefficient, has been degraded here. So why does this make sense? Well, if xi can be predicted well from the other predictors, we know ri squared is large, and the value for the standard error is going to be big. Xi is highly correlated with the other predictors. So why is that standard error large? Well, if the correlation between xi and the other predictors is big, that's going to make it difficult for the model to really disentangle what variation in y can be attributed to differences in just xi, and what variation in y can be attributed to differences in other predictors. So if we go back and look at that interpretation of the coefficient, the interpretation of bi is that's the expected difference in the y values among individuals who differ in xi by 1 unit, but who are otherwise identical. So when we have a lot of correlation going on between xi and the other predictors, it's very difficult for the model to envision individuals that differ only in xi by 1 unit, but who have identical values for the other x's. Those individuals just don't really exist in the data set, so the model has difficulty kind of nailing down what this number is. So we quantify how much the standard error has been degraded due to correlation in the predictors with the VIF. And the larger the value of VIF, the poorer estimated the coefficient is, relative to the case where all the predictors were independent. So, for instance, a VIF of 5 indicates that the information contained in xi is pretty redundant with the information contained in the other predictors. VIF of 5 means that ri squared would be 80%, so basically 80% of the information contained in x is represented somehow by the other predictors, and so a lot of that information is redundant. The standard error of xi is the square root of the VIF, square root of 5, or 2.2 times larger than what it would have been had all the predictors been independent. So how big a VIF is too big? Well, my guideline is to calculate 1 over 1 minus r squared, where r squared is the r squared of the multiple regression model, not r squared adjusted. If the VIF is bigger than this number, the predictors are doing a better job at predicting xi than they are doing y, and that's a bit awkward. So if we have a large number of predictors with large VIFs, we say the model suffers from multicollinearity. What's the consequence? Well, it's actually not too bad. Multicollinearity doesn't invalidate a regression model. Multicollinearity just means that the correlation in the predictors is large enough that the model's having trouble estimating the coefficients. The standard errors of the coefficients are a lot bigger than what they would have been had all the predictors been independent. So for descriptive modeling, that's bad news because we want to estimate those coefficients as precisely as possible. For predictive modeling, we don't really care. Actually, multicollinearity doesn't degrade our predictions all that well. All right, so the slide's a bit out of place. What do we do with influential points? Back when we were discussing the points that had more than their fair share over determining those coefficients, we make sure that there aren't any issues with those points, no typos, because we don't just haphazardly throw away points unless we have a really good reason to. All right, some extensions to the multiple regression model if we see that the assumptions don't quite hold up or if we think the relationships might be more complex. Instead of just having x be a predictor in the model, we might actually try a polynomial model in x. Basically add x, x squared, x cubed, all the way up to xm, m being the order of the polynomial, as predictors into the model. And this can solve the problem when we see curvature in the relationship between y and x. And so the strategy is to fit a whole bunch of polynomial models and choose the simplest model that has a very high R-squared adjusted. So R-squared adjusted is our measure for comparing multiple regression models. Higher is better, but simplicity is also good, so we find the polynomial model with the highest R-squared adjusted and then choose the simplest one we can get away with, the simplest one whose R-squared adjusted is at most 0.005 below. One very important extension for multiple regression is considering interactions between variables. Because we know that when we interpret the coefficient in a regression model, beta I is the expected difference in y between two individuals that differ in xi by 1 unit, but whose other values for the x's are the same. And along with that interpretation is that that expected difference in y is the same regardless of what those other predictors actually equal to. Big values, small values, it didn't matter. As long as those two individuals differed in xi by 1 unit, but who were otherwise identical, that expected difference in y values is always the same. And that's not always the case, because sometimes the strength of the relationship between, say, y and x1 might be different for individuals with varying values of x2. And so our solution is to consider adding actually an additional variable, an additional predictor, to be the product of two different variables. This is called the interaction term. And it allows us to add an extra layer of complexity and reality to a model. So what does adding this term do for us? Well, let's actually look to see what the relationship between y and x1 looks like for various values of x2. So we can write out the implicit regression equation, basically plug in particular values of a predictor, and look to see the result. So if I fit this model, then what the model is implying that if I look at just individuals with x2 is equal to 0, plug in x2 equal to 0 here, my relationship between y and x1 looks like this. Y is equal to beta 0 plus beta 1 times x1. Now, when x2 is equal to 5, plugging in 5 whenever I see x2, and then just grouping terms, I find that my equation is y equals to beta 0 plus 5 times beta 2 plus beta 1 plus 5 times beta 3 times x1. So this is great. So one thing I notice is that the effective coefficient of x1 here is beta 1 plus 5 beta 3 when x2 is equal to 5. The coefficient of x1 when x2 is equal to 0 is just beta 1. So the coefficients of x are kind of allowed to depend on what x2 value I'm actually talking about. And this allows me to do two things. First of all, this coefficient talks about how strong the relationship is between y and x. Values farther from 0 indicate stronger relationships. So being allowed to have different coefficients means that I'm allowed to have the strength of the relationship between y and x1 vary depending on the x2 values of the individuals I'm looking at. And it also allows me to have the difference in the expected values of y when I compare two individuals that differ in x1 by 1 unit to sometimes be large and sometimes be small. The coefficient is telling me the expected difference in y values between two individuals that differ in x1 by 1 unit. And so I see that, when x2 is equal to 5, this is my expected difference. When x2 is equal to 0, this is my expected difference. They're allowed to have different values for that expected difference. So how do we process and study an interaction? Well, we start out by writing out the regression equation. and then just plugging in values for one of the variables to see how that relationship changes, looking at those implicit regression equations. So here's my equation relating salary to education, experience, and their interaction. I'm plugging in experience equals to 0 and honing in on the relationship between salary and education. I find that among people with experience equal to 0, my equation is salary is equal to 2841 plus 150 times education. So two individuals that differ in education by 1 year but who both have no experience are expected to differ in salaries by $150. And because there's an interaction, that story is going to change if I consider a different value of experience. So if I write out that equation for individuals with 10 years of experience, just plugging in 10 wherever I see experience and then combining terms, I find that the equation of salary is equal to 2461 plus 90 times education. So if I compare two individuals who differ in education by 1 year, but who have 10 years of experience, I expect the difference in salaries to only be $90. So that difference is smaller among individuals that are more highly experienced than when they were very fresh out of high school, no years of experience there. So by having that interaction in there, I've allowed the expected difference in salaries between two individuals that differ in education by 1 year to actually sometimes be large and sometimes be small, depending on what experience level I'm comparing. So writing out the regression equations allows you to kind of talk about the relationship between y and x for particular values of that other variable. The interaction plots show the same story as well. So what do you need to be able to do? Well, you need to be able to look at one of these interaction plots and actually describe how the nature of the relationship between y and x varies depending on the values of the other variable. So here, it's the relationship between salary and education for individuals with small experience in blue, median amounts of experience in black, and large amounts of experience in red. And so what we see is that the relationship starts out fairly strong and positive between salary and education when the experience values of those individuals are very low. And as we compare progressively more experienced individuals, go from blue to black to red, we see that the strength of the relationship diminishes. In other words, the importance of education to salary gets smaller and smaller as we're comparing individuals with progressively more and more experience. Kind of implying that, hey, it's really only experience or only education that matters. If you have a large amount of one of them, it doesn't really matter if you have large or small amounts of the other. All right, so how do we know when an interaction is important? Well, by looking at the interaction plots, we look to see, does the nature of the relationship change much between y and x1 as we vary the x2 value of the individuals? In this case, no, the slope of the line is essentially the same, so we would say that x1 and x2 don't really have an interaction. The nature of the relationship between y and x1 is the same, regardless of the x2 values of the individuals. Same story looking at it from the y versus x2 perspective. This interaction plot shows that the interaction is probably important because we see that the slope of the relationship between y and x1 changes actually quite a bit depending on the x2 values of the individuals we're looking at. What we see is that the relationship between y and x1 gets stronger and stronger as we compare individuals with progressively larger values of x2. Because we start out with the blue line, move to the black line, move to the red line as x2 starts out small, median, and large, and we see the slope of that just getting farther away from 0. So the strength of the relationship between y and x1 gets even stronger as we look at values of x2 that are larger. Likewise, for this one, we see the nature of the relationship between y and x2 changes depending on the x1 value of the individuals. We see that at small values of x1, the relationship between y and x2 is somewhat negative, and for very large values of x1, the relationship is actually somewhat positive. So the whole nature of that relationship changes. So what do you need to be able to do? You need to be able to write out that multiple regression equation from the R output, and then write out the implicit regression equations for some particular values of one of the variables of interest. And you'll need to comment on how the strength of that relationship changes between y and x1 as we look at different values of x2. And also I want you to be able to do that from looking at the interaction plot. And one additional thing that I want you to be able to do is comment on how the expected difference in y between two individuals who differ in x1 by 1 unit, how that difference changes as we vary the x2 values of the individuals. So you can get that pretty easily just by looking at the numerical values of the effective coefficients of x1 as we plug in different values of x2 into the equation. But you can also get that graphically. So here, if I hone in on small values of x2 here, I see this much variation in y values between the individuals with different values of x1. And for large values of x2, I see a pretty large spread in y values depending on the individual's values of x1. So the spread in y values is relatively small when I look at individuals with small values of x2, and it's fairly large when I look at large values of x2. Likewise, going back to salary here, when we compare individuals with very little experience, I see a wide range in salaries depending on what the education is. And when I look at large amounts of experience, I see a fairly small range of salaries. In fact, I also see something kind of interesting. At very small levels of experience, what I see is that people with the highest levels of education tend to have the highest salaries. But when I compare people that are super educated with 30 years of education, I actually see the individual with the largest amounts of education actually have the smallest salaries of the three possible values for education here. All right, so we can kind of update the interpretation of our coefficient. Same old interpretation when xi is not involved in an interaction. But when xi is involved in an interaction, we actually can't interpret the coefficient anymore unless we're given additional information. That's because the expected difference in y between two individuals that differ in xi by 1 unit is no longer a constant, but it depends on the exact values of the variables with which it is involved with in an interaction. And those values have to be specified before making any further comment.